We will move to the next speaker. Please, Professor Carmel Majidi, please share your screen. So Professor Carmel Majidi is working at CMU. He's also a pioneer in soft robotics. He received numerous awards and grants, and in particular, I think he received almost all the early career awards from the U.S. funding agency, including DARPA, Air Force, NASA, and many others. And the stage is yours. Thank you, please.
Yeah, thank you very much for the warm introduction. It's a pleasure to be part of this workshop. So, thank you, Hao, and the rest of the organizers for putting this together. This has been great so far. So I'm going to present work that my lab has been doing on trying to build untethered soft robots. So as Nathan discussed before in his earlier lightning talk, I mean, this has been a challenge in the field of soft robotics, and both for the larger types of systems that Nathan presented, but also for these smaller robotic systems as well. And for my group, I mean, a big source of inspiration has been for a lot of people working in the field of soft robotics have been soft marine organisms that are capable of just really extraordinary functionalities, largely with soft materials. And so here's an example of a octopus coming out of a beer bottle. I'm sure you've seen plenty of other videos of octopuses doing amazing things. Really the best that we've come, at least in our lab so far, is this next clip here, which is our not quite octopus-inspired, but more brittle starfish-inspired robot that we call Patrick. And so I'll, in this presentation, just kind of go through the steps and the iterations that brought us to this point. And so Patrick is a fully untethered robot. It's powered using shape memory alloy actuators. There is onboard electronics for power regulation, control, and also you can see that little antenna sticking out. And so there's wireless interfacing there, but there's not yet onboard sensing, and so that kind of represents an open challenge for us. So I'll talk about what brought us here and also kind of what the next steps are for us in terms of making the robots like Patrick fully autonomous and not just untethered. So why untethered soft robots? Well, one is this kind of grand challenge or this ultimate goal of fully autonomous soft robots, but in the near term, we're also interested in engineering soft robots to function as test beds to experimentally validate some of the soft robot physics engines that we're developing. So here's a few clips here showing different types of robot implementations that we've built in the lab and some validation we've done of a physics engine that we're co-developing with collaborators at UCLA. So this is work led by Khaled Jawed over in the MAE department there. So that's one area where we want these robots to be untethered so that the tether doesn't interfere with the fidelity of the robot locomotion and mechanics. Another is that these robots can function as platforms for evaluating novel types of sensors and control schemes. And then kind of going beyond even robotics, I mean, these test beds could also be used to better understand natural organisms and also explore broader questions within bio-inspired engineering. So for us, I mean, building these types of soft robots, untethered soft robots, has been kind of more of a comprehensive type effort. So there's been work on the actuation side and also on the sensing side. I'll just kind of start by talking about some of the considerations in actuation. So there's quite a lot of different architectures that we've seen in these talks for powering soft robots. And among these, we've actually had the most success with shape memory alloy. And a lot of this work was actually inspired from my experiences back as a PhD student working in Professor Ron Fearing's group, where they were able to create all sorts of untethered, not quite soft robots, but highly compliant and miniaturized milliscale robots powered with shape memory alloy. And so firsthand, I saw, even though I wasn't doing research in that space, I could see firsthand how effective SMA is for achieving these battery-powered robots. Now, of course, there's limitations with shape memory alloy, and generally there's pros and cons with all these different mechanisms for actuation, as we've been learning in this workshop. But starting out, I felt SMAs are good enough. However, we started hitting some bottlenecks, and so this is kind of an early attempt at a SMA-powered compliant robot, which this is a real-time video, and you can see it's quite slow. Basically the power requirements or the battery requirements necessary to kind of power all these SMA coils, which you can't really see here, but are kind of tucked in here. Actually, each one of these lugs has 2 coils. So there's one here, if you can faintly see, and then another SMA coil there. But the robot wasn't able to kind of support the weight of all the microcontroller, the PCB board, and also the battery. And so this was an early kind of fully tethered implementation. Soon after, we discovered that there was a more optimal way. I use the term optimal here very loosely to create actuators that were a little bit faster, a little bit more robust. And the way we achieved that was to take a wire of that shape memory alloy, loop it around, stick it between 2 films of thermally conductive rubber. One of the films of rubber was pre-stretched, and so that would induce a residual curvature. And when we pass electrical current through the SMA, that causes the SMA to go from being fairly malleable and compliant to being very rigid, and it'll want to straighten out. And in doing so, it'll cause this kicking motion. You can kind of see it here with this kind of single kind of soft robot limb. And so the hope was that with this fairly dynamic, high force output motion, we might be able to create robots that are a little bit more load bearing and also faster, so we can create these fully untethered soft robots. And so we did some characterization and then did some implementations here. So I'll just show you videos in the next slide of a soft robot quadruped and also a caterpillar, where you can see where we can make these fully untethered. All these LiPo batteries are just kind of stacked on top. We just use a flex circuit here for control and power management. And again, each one of these limbs here is basically that SMA wire that's kind of looped and sandwiched between these thermally conductive rubber sheets. And so these are real-time videos. I'll just turn the volume off. And you can see that we get motions that actually start approaching the walking speeds of some biological organisms. And so we're not quite at 1 body length a second, but we are kind of at the cusp of that. And we have actually had, since these videos were taken, some implementations where we were kind of getting motion at a body length a second. So if you kind of compare where these soft robots are compared to biological organisms, still there's quite a ways to go in achieving biologically relevant walking and running speeds, but there is good kind of progress and certainly improvements over past work with pneumatically powered untethered soft robots. So a next step for us was to see now if we could create a swing version of these untethered soft robots using the same shape memory alloy architecture. So here's kind of an early attempt. And again, we're a little bit back to square one here. I mean, in this case, we have 8 of these actuators are kind of arranged in this kind of radial type pattern. And yeah, it looks fast at 10x, but at 1x, I mean, you can see that the speeds aren't really kind of enough to use this as a test bed to either examine natural biological swimming, say of a starfish, or for that matter, using this for any kind of validation of a soft robot physics engine, just because this motion doesn't really kind of capture the dynamics and hydrodynamics of what we would want in a physics engine for that kind of modeling. So next attempt was to switch up the design, and so instead of having the wires operate in that flexural mode, we had them operate in this linear kind of contracting mode, but the swimming speed was even worse. I haven't put the timestamps here, but it was pretty abysmal in terms of the ability of this swimmer to kind of move across in this water bath. And so finally, we converged on this third version, which is where we are currently. We replaced the straight SMA wires with coils. And this was, I mean, tons of folks have kind of, adopted these SMA coils for artificial muscles. We were particularly inspired by work from Bristol University. Of course, Barry Trimmer has done a lot of, really exciting work using a similar architecture. Now, one variation compared to what was done at Bristol is that instead of having just 2 antagonistic coils on either side of this flexure, we actually have 4, and that allows us for having bending just both in the plane but also out of the plane. And so that's what we used here, and you can kind of see it's a little bit difficult from this top-down view, but this the limb is not just kind of bending side to side, but it's also kind of bending up and down, and that ends up being critical to capture another mode of locomotion for starfish and brittle star, which is that, not just that these organisms don't only paddle, but they also kind of crawl along the seabed, and so they kind of have this somewhat of a kind of a crawling or walking gait. Other features of this, we have our onboard battery. Like I mentioned before, there was an antenna kind of sticking out that's kind of semi-submerged in the water bath, and that allows for radio communication over Bluetooth. And so we have a Nordic microcontroller, so it's a module that has both the processor for the control, but also the wireless module there for offboard communication. And then we have MOSFETs to regulate the power delivered to all 20 of these SMA coils. So each limb has 4 coils, and we have 5 limbs for a robot. And then for the closed loop control, we have this offboard. We have this battery just set up over the water tank. And so that's shown here. So we just go immerse Patrick, and there's the camera above. And then we just use very simple computer vision just to do tracking of Patrick and also tracking of the obstacle or the target. And so we just perform some similar, very simple target following tasks here. And to aid in that, we also did some calibration to come up with some simple motion primitives. So based on where the robot is in relation to this target, it can basically perform path planning based on those simple motion primitives. And so it's not great. I mean, plenty of room for improvement here, but it eventually will kind of find the target with the aid of the computer vision and then go and start crawling towards it. And as that target moves, the robot will adapt its path accordingly. And so I'll let this video play out just a little bit. In a few seconds here, you'll see that as we move this target, the robot will then reverse course. Right, so, and because of just the kind of the axisymmetric kind of star-shaped nature of this robot, it has this kind of omnidirectional properties. So it doesn't really have a front or a back. It can easily kind of maneuver and turn as needed to follow the object. Okay, so that's the kind of the robot in terms of the actuation, but the sensing is all done off-board with that camera. And so the next step for us is to do onboard sensing. And something that an approach that we think could be very promising is to use liquid metal for not just the kind of electronics and circuitry, but also for the sensing. So here's some kind of early examples here of work that we've done in the past with creating, in this case, a stretch sensor using a liquid metal channel inside rubber. This is a 9-axis IMU along with a temperature sensor. So these are microelectronic chips. But the wiring is all achieved with liquid metal. And the hope is that because we're using liquid metal, that will be more compatible with the silicone rubber that we use for the body and the limbs of the soft robot. So we can drop in these microelectronic chips and just use liquid metal wiring and avoid the need to put in rigid PCBs or flex PCBs along the limb. So the purpose here is just to preserve the overall mechanics of the limbs of the robot. And to kind of demonstrate that, we did kind of a simpler implementation on a kind of underwater soft robot gripper, where we created this electronic skin with all these different microelectronic chips embedded inside, and again with this liquid metal wiring to connect all the pins. And the skin is fairly soft, flexible, stretchable. It conforms easily to that soft robot gripper. Again, here we use coiled SMA for the actuation. And with that elastomer sealing, this electronic skin and gripper can function underwater And then out of water, here we demonstrate just the different sensing modalities. And so with this gripper, in this case, we have pressure sensors on the left and right finger. We have a time of flight sensor for object detection. And we're able to detect the location of objects, and then basically command the gripper to go in and grasp the object and perform just simple pick and place tasks. And in the next clip here, I'll just show in the case where, say, we were to knock out that object. So here's another object where, again, it grips it. We pick it up. Oh. And now what we're going to do is remove it, and then automatically the gripper is going to detect from the pressure sensors that the object has been removed. And so now it'll go to rescan for the object. And so all of this is done kind of just through a simple Markov a sequence, but it doesn't require any kind of manual intervention. So that's the kind of idea moving forward with incorporating sensing so that we could eventually have fully autonomous robots. Another kind of a challenge for us is the fact that these SMA coils are pretty power hungry. And so with our onboard lithium polymer battery, for the Patrick, we use this drone battery, and we pretty much use that up in about 10 to 30 minutes. And so in some sense, these SMA coils are kind of a surrogate for other type of artificial muscle actuators, better ones that could come along in the pipeline. So we're really eager to collaborate and kind of utilize whatever it is that you've had success with. As far as kind of, autonomy, untethered is not enough, right? I mean, we're going to have to get onboard sensing for proprioception, motion tracking, monitoring the environment. Also, we're going to have more capabilities for onboard computing for decision making. So right now, the controller we're using is just getting messages from an offboard computer in terms of what locomotion gates to execute. So all that should be done onboard. And we also need to find kind of more compelling use cases where we actually do need software bot autonomy. So that's it. I'll just close by acknowledging sponsors and the research lab, and there might be time for a few questions here.
Yeah, thank you for the impressive work and inspiring talk. I think for audience, if you have a question, please post in the Q&A box, and we can, due to the time limit, Professor Majidi can answer that through the chat box.